we have our lovely picture, and I'm not going to review it because we reviewed it 2 seconds ago. But, oh, what the hell, I am going to review it. Okay, so we have our A, it's n by m, right? And so far we know that over here on the left-hand side we have Rm, that's our domain space. Over here on the right-hand side we have Rn, that's our codomain space. We know that this piece is the column space, which is the same as the range, and it lives on the right-hand side of the picture because we did A to get over there. And when we were thinking about that, we were using the column multiplication picture, right? So we also know that 0 goes to 0, because when you take a matrix and multiply by the 0 vector, you get the 0 vector. Now our question for kind of our next piece is going to be, what other things go to 0 over there? Are you on board with that? So when I think about what things go to 0, I'm going to start by naming that thing. And the symbol I'm going to use is just a capital N. So I'm going to say this is n of A. And what we're going to talk about n of A, so n of A is going to be the set of things, that's going to be the vectors, in, where are my vectors going to live? So this thing, so far, I've just labeled it arbitrarily. This is probably a bad idea, but hopefully it'll work out. So right now it's on the which side of the picture? Yeah, it's in the domain side of the picture, which means that any vector that's in n of A is going to have to be a member of, yeah, it's going to have to be a piece of Rm. And when I apply A to it, it's going to end up in the codomain. Are you on board with that? So I'm going to say this space, n of A, I'm going to call it null space. So when we say this, it's going to be null space. And I've got a little bit of work to earn that name. What's the work I'm going to have to do to earn that name? Yeah, but there's one specific piece of work I'm going to have to do to earn the space part of this name. Yeah, I got to check whether it's actually a space. It's already part of a vector space, right? So I'm only going to have to check whether it's a subspace or not. Same way we did with the column space. So I'm going to call it a null space for now. That name's provisional until we're done. I've got X, which is in Rm. So we're going to say the null space is all the vectors in Rm such that A done to that vector gives us the 0 vector. So I'm essentially revising this big old arrow, right? That I know 0 goes to 0, and I'm also going to say whatever else happens here, all of this stuff goes to 0. Get on board with that? So, I guess first things first, we should probably figure out if it's a space, right?
When it goes there, if it all goes to 0, when it gets back to that point, does it start spreading the vectors back out?
Oh, like if we're coming from the right side of the picture back to the left? Yeah, that's why my inverse here is in this kind of very light, hopefully hard to read on the video text. My goal is to make you think that that probably doesn't exist. And in the case that the null space is anything interesting at all, that won't exist. Because if there are any vectors in here that aren't just the 0 vector, like, in other words, if this box has any size to it at all, then the inverse won't exist. Because I can't undo the crushing that I just did. Right? I would have to have a 2-to-1 map to come back, and that isn't a thing we do. Right? That make sense? So this is going to be another criteria for invertibility, actually. If a matrix is square, and the null space is only the 0 vector, I'm going to be able to come back. Bonus fact. So let's get our space thing. We need to check 3 things. What's the first one? Good. Is the 0 vector in it? So, does the 0 vector go to 0 after you apply A? Yeah. We actually talked about that earlier. It's so incredibly obvious that this feels a little hard to check. Like, were you asking a question or telling me a thing I already knew? Like, okay. Alright, so for thing 1, I need to check closed under what? Okay. So to check closed under vector addition, I need to do something like let x be an n of a and y be an n of a. Right, so letting x and y both be in the null space. What does that mean? If x is in the null space, what can I say? Yeah, I know that when I do a to it, I get the 0 vector. So this statement is the same as the statement ax equals 0. And the statement y is in the null space is the same as ay equals 0. On board with those? Okay, so then I want to do a to x plus y. Why do I want to do a to x plus y?
Just the x, y are your vectors in the space, or in the matrix of A.
Okay, so if I'm checking if it's closed under vector addition, right? I need to add x and y, and then I need to know if those are in the null space. So to know if they're in the null space, I have to do a to them and see if I get 0. On board with that? The bad news is I don't really know much about x and y. I also don't really know much about the matrix A because I'm trying to do a really general thing, right? The good news is that I know enough. So when I'm doing a to a sum, I can split that into ax plus ay. Why can I do that? Yeah, there's a distributive property of matrix multiplication. Alternatively, matrices are linear operators. Those are actually like 2 sides of the exact same fact. They're just set in different ways. And they're both exactly the exponents. So, linearity of the matrix operator lets me distribute. Cool. Now what? What do I know about ax and ay? Yeah, I know both of those are 0. So I get the 0 vector plus the 0 vector, which is, lo and behold, the 0 vector, and check. Right? Yeah, this is why the null space is really casual, because there's lots of zeros involved. Finding it's a little harder, but once you've found it, it's pretty chill. Okay, so I got closed under addition because when I added 2 vectors that were in the null space, I did a to them, I got 0. That means that x plus y is in the null space. You on board? Okay, second thing. I need to check closed under scalar multiplication. Okay, so to check closed under scalar multiplication, I'm going to let x be in n of a, right? So x is going to be in the null space. Again, that means that a done to x is 0. And I'm going to let c be in R. And I feel like I'm running out of space, but the good news is this argument doesn't take any space. Because I need to do a to what? Yeah, I need to do a to cx. And I can take that scalar out because this is kind of the, yeah, this is a commutative property actually. This is the commutative property of scalar multiplication and matrix multiplication. Or you could say it's because matrix is a linear operator, which is way easier. So I would say I'm taking the C out because matrix is a linear operator. And now I know what AX is. What's AX? AX is 0. So I get C times the 0 vector, which is still the 0 vector. And we can put a big old fat check mark on that. And the null space is indeed a space. Get on board with this? Okay. As a quick bonus, let's name the other two spaces. And then we'll have to show that they don't overlap a bit. So right now I've got them drawn in such a way that there's a right angle here and they only overlap with the 0 vector. And that's not going to be in evidence right away, but let's name them and then we'll work that out at a later time. So if A goes from this side to that side and has a null space over here and a column space over there, A transpose goes from this side to that side and is going to have a null space over here and a column space over here. Right? Okay. The cool thing is the null space of A transpose is just this guy down here. So it's the kind of complementary space of the column space of A. And the column space of A transpose is going to be this fellow right here. So this guy's going to be the column space of A transpose. And the thing is, that's not actually the way I'm going to write it most of the time. So it's going to take a hot second. What are the columns of A transpose called when they're in A?
The rows.
Yeah, they're the rows of A. Is all on board with that? So instead of calling this the column space of A transpose, most of the time I'm going to call this the row space of A. Are you on board with this? Okay. Now, we still have some work to do in order to say that our picture is kind of complete, and we haven't really understood fully the implications yet. We're going to get to that. But right now we have some cool stuff. We've got labels on everything. We know that the null space of A is a space. We know the column space of A is a space. Do I know that the null space of A transpose is a space? Yeah, it has to be. Why does it have to be a space?
Because N of A is a space.
Yeah, because N of A is a space, and N of A, like, the argument that I used for N of A was just about a matrix at all, right? And A transpose is a matrix at all. The thing I don't know is that they only overlap at 0 right now. Like, I don't know that. It is entirely possible, with what I know right now, that these two spaces could be like more intermixed than they are. We're going to figure out that they're not, but they could be. Why do I know that row space is a space?
Column space that is
Yeah, because it's the column space of the A transpose matrix, and my argument about the column space being a space only relied on the fact that A was a matrix, not on the fact that it wasn't the transpose of something. Does that make sense? Like, the transpose of a matrix is still a matrix, and I demonstrated that the column space of a matrix is a space, regardless. So again, I still don't know that these aren't like a little more overlapped. I do know that they both contain the 0 vector, because the 0 vector goes to 0, and the 0 vector is something that I can make out of the columns of A transpose.
So like wherever the vectors are cutting them off.
Oh yeah, so
You can't really.
yeah, it does have to be a little bit clear here that I'm drawing a picture of high-dimensional space, and I'm using a two-dimensional picture of it. So, in general, what might happen is this might be a 4-dimensional piece of R7, and this might be the other 3-dimensional piece of R7. I am going to demonstrate they do intersect at a right angle, and we are going to demonstrate that they have to kind of count up in the right way. That this dimensionality plus this one has to match this. But we're not there yet. It's going to take a couple days. Overloaded on information for right now.